We're going to go back to the frequency domain now. The frequency domain is useful not only for talking about sampling theory, but for describing sounds and signal processing on audio, synthesis algorithms. We'll be using the frequency domain throughout the course as a way of visualizing signals and their content. So in this talk, I'm going to show some examples of simple spectra. I will talk about the difference between Fourier transform and the short-term Fourier transform. I will show you the discrete Fourier transform and the fast Fourier transform. We'll talk about windowing, and we'll actually take some spectrum measurements with Audacity. This is the formal definition of the Fourier transform. Just for review, we've seen the real and imaginary part as separate functions using cosine and sine functions. We've also put them together into the complex Fourier transform, which is a single equation describing the Fourier transform as a complex function of frequency. Let's look at some examples. So in all these examples, the horizontal axis here is frequency. The vertical axis is amplitude. Notice that we've ignored phase here, so we're only talking about amplitude. And the first example is a sinusoid. So as you would expect, the sine only has energy at one frequency, which is this point, and the amplitude of this impulse describes the amplitude of the sinusoid. So let's play a sine. So what do you think would happen to this picture if the amplitude was greater? Well, this impulse would be taller because the amplitude would be higher, and vertical is the amplitude axis. If the sinusoid had a higher frequency, we would still expect to see one impulse, but the impulse would move up towards higher frequencies along the frequency axis. The next example is noise. Let's play some noise. So this is white noise, meaning equal amplitude at all frequencies. And so the spectrum has constant amplitude but energy at all frequencies. The next example is a tone with harmonics. So we've looked at tones and harmonics before. Now it should be really clear that in the frequency domain, the fundamental frequency is represented by this impulse at a specific frequency, and the harmonic components or partials are at multiples of this fundamental frequency. So this is kind of a classic looking spectrum for a sound with perceived pitch, and we can play that. Again, if the pitch went up on this signal, you would expect this entire spectrum to be stretched. The fundamental frequency would go up by some increment. The second harmonic would go up by twice that increment because we're doubling the fundamental frequency, and so on. But you would still have this kind of general shape. The next example is narrowband noise. What do I mean by that? Well, let's play something. So this is not white noise. This is noise that has some kind of resonance or concentration at some frequency. And the spectrum for that is where the frequency where the energy is concentrated, but energy all around it. Here's another example. Now this last one was obviously a very high frequency resonance noise. So you would expect that this concentration of energy would move up in the frequency domain and be located somewhere over here. Finally, an impulse. An impulse is in the time domain is just a click or a pulse that goes up and comes down immediately, and as the pulse width goes to 0, the the spectrum goes to containing infinitely many frequencies, and it's perfectly flat. So it looks exactly like the spectrum of noise. How can that be? Well, the difference between noise and an impulse is noise has random phase, and an impulse, the phases are very sort of carefully determined in order for all those different frequencies to pile up at one point in time and result in an impulse. So I'll play the impulse will sound like a click. Let me play that again. Okay. We've talked about negative frequencies before and glossed over them to a large extent. So let's say a little more about negative frequencies, which is often a confusing point. You know, what does a negative frequency mean? Well, we've used omega to be frequency. So when we take omega times time, we get an increasing phase, and if we take cosine of that, we'll get a cosine wave. So negative frequency just means that we replace omega with negative omega. Physically, it doesn't really mean anything specific, so it's more of a mathematical construct, as if time were running backwards, maybe. And notice that cosine of omega t is equal to cosine of minus omega t. So when we do those integrals with cosine, it doesn't really matter if we put a negative sign in front of omega, because we get the same answer. In a similar vein, sine of omega t equals minus sine of minus omega t. So when we compute the imaginary part of the Fourier transform, the negative frequencies are going to be just the negative of the positive frequencies. So we have these symmetries with the Fourier transform. On the imaginary part, we have odd symmetry, meaning that the positive frequencies are the negative of the negative frequencies. The real part has even symmetry, meaning that the positive frequencies are equal to the negative frequencies. And because of this symmetry, negative frequency information is completely redundant. This is for the analysis of real signals, which is what we're doing. Because of this redundancy, we don't really have to look at the negative frequencies, and that's why we mostly just ignore them. They're really there because it allows us to talk about integrals from minus infinity to plus infinity rather than starting the integrals at 0. There's just some mathematical simplification there. Now let's talk about the short-term transform. In practice, we can't do infinite time integrals on signals, and oftentimes we want to know what's going on in a signal within a shorter time duration. And so we can do a finite integral. So we do the same Fourier transform equation, except rather than going minus infinity to plus infinity, we go from A to B over some specific time interval. So when you do that, you end up with almost all of the interesting properties of the true Fourier transform, but there are some annoying artifacts having to do with these hard boundaries, and we'll talk more about that later. Another variation is the discrete Fourier transform. We cannot actually compute on continuous signals. Digitally, we only have sampled signals. And so we need a discrete version of the Fourier transform. This is called the DFT, discrete Fourier transform. And it is essentially just like the Fourier transform, except that the spectrum is band limited. And if we're dealing with a short-term discrete Fourier transform, then we have a finite amount of data, and so we can actually compute it. So I'm glossing over many derivatives, derivations, and proofs and details here. I apologize for that. There are many books about Fourier transform that This is typically covered in college linear systems courses, so the information is out there, but there's just too much to go into great detail for this course. Next, I'm sure you've heard of the fast Fourier transform, or FFT. What is that? Well, the short-term discrete Fourier transform is described by this equation. This is, we've taken f from a functional notation, f of omega, to f of k, to indicate that we're dealing with discrete samples. And we've taken the real-time function, which used to be f of t, and replaced it by f sub n to indicate that this is a sampled function. And we've taken the integral and replaced it by a summation sign, again, because we're dealing with a finite number of points. And the complex exponential here is analogous to the continuous time version, but it's obviously, instead of continuous time, the parameter is n, which is the index of this summation. Okay, so this is what the discrete Fourier transform looks like. This is what we actually turn into an algorithm and compute when we're computing Fourier transforms on a computer. And looking at this, what's the complexity here? Well, for each value of k, we have to run through all of the samples of this time interval. And how many values of k are there? Well, it turns out there are as many values of k as there are samples being analyzed. So this seems like an n-squared problem. For each value of k, we sum up a function of each sample. Classic nested loop, n-squared. Now, it turns out that there's a very clever way to restructure this computation and get the total number of computation steps down to something proportional to n log n, much faster than n squared, and that's called the fast Fourier transform. Computes the same answer, modulo rounding, but it's faster. When we compute these short-term Fourier transforms, what we're doing is we're slicing out a segment of the signal to be analyzed and computing the Fourier transform over that little slice. Now, the problem with this is that the slice begins abruptly and it ends abruptly. It's as if we took the continuous signal and we multiplied it by a square pulse that it goes from 0 to 1, stays at 1, goes back to 0. And, this multiplication by a square pulse is actually going to change the spectrum. There are various ways of looking at it, but no matter how you look at it, the spectrum is adversely affected by taking out this slice and analyzing it all by itself. So one way to soften the artifacts that we get here is to pre-multiply this segment by what we call a smoothing window. It looks kind of like this. So this function starts at 0, it smoothly goes up to a peak in the middle, and then smoothly goes back to 0. And what that's doing is, well, here's the product on the right. What that's doing is making the signal smoothly go from 0 to a signal with some spectral energy and back to 0 again, and avoiding or removing any sudden transition, which would imply a lot of extra spectral energy. These windows come in different shapes, optimized for different properties, and so you'll see names like Hamming window, Hanning window, Blackman window, and so on. But the important thing is that when we compute spectra, discrete Fourier transforms, we almost always multiply by a smoothing window to remove some of the artifacts that we would otherwise get. Now I'd like to use Audacity to show you some spectral analysis of some real signals. I'll switch to Audacity. we're going to record something. So let's record some noise. Shh. And let's record a tone. Tone. And let's record an impulse by clapping. That looks pretty good. Okay. I'll go back to find the noise. And let's go up to the Analyze menu and choose Plot Spectrum. Now I'm going to choose the size to be 4096. That's the number of samples in the analysis window. And I'm going to stretch this window out as much as I can so we can kind of focus in on the lower frequencies. There we go. And so you see, you know, if this were perfect white noise and everything was perfect, we'd see energy from 0 up to the full spectrum, and it would all be flat. We don't see that, partly because I think the microphone and maybe my mouth are not dealing with low frequencies particularly. There's some variation in high frequencies here, but generally you see lots of energy across the spectrum. It's all pretty random looking. No particular peaks except up at these high frequencies, and maybe these were resonances due to my mouth or the microphone placement. So let's get rid of that and go over to the tone. So I'll pick a steady part of the tone. Okay, it almost doesn't sound vocal when you grab the middle part. And here we'll do Plot Spectrum. Wow, and we get a very different looking spectrum here. So now we can see these many peaks. Each one of these peaks represents a harmonic of the fundamental, which is down here somewhere. And you notice that the peaks are not of uniform amplitude. Partly this is because this is a vocal sound and we have some resonances, but we'll learn more about that later. The important point is we have a series of harmonic partials. Okay, and then we go to the clap. So remember, the clap is sort of like an impulse, and we expect to see a broad spectrum. So we'll see what happens here. Yeah, a very broad spectrum, more or less flat. Of course, you know, there are, it's higher in some places and lower in other places, but the overall shape compared to other things we've seen is a broad, flat spectrum.